In a system of linear equations Ax equal to b, the left-hand side can be viewed as the output of some mapping T with input x. Remember that Ax is simply a tuple, and each entry of this tuple is of the form a1x1 plus a2x2 plus all the way to an xn, where a1 up to an are constants, and so this is a linear function in x1 up to xn. And we say that T is a linear transformation. We'll actually talk about linear transformation in more detail later on. But for now, it is sufficient to know that any linear transformation T that maps n tuples to m tuples can be written as T of x equals Ax for some matrix A with m rows and n columns. For example, if T is given by the following, then T of x can be written as Ax with A equals 1, 2, 3 in the first column and 4, 5, 6 in the second column. If T of x1, x2, x3 is given by this, that is, T maps the third component into the first component into the second component, and the second component in the third component, we can still give a matrix A. And rewriting this output in the following manner, the matrix will become clear. So x3 is simply 0 times x1 plus 0 times x2 plus 1x3, and x1 is 1x1 plus 0x2 plus 0x3, and x2 is 0x1 plus 1x2 plus 0x3. And so the matrix is simply 0, 0, 1, 1, 0, 0, and 0, 1, 0. So with this view, we can interpret this system of equations as finding inputs x such that T of x is equal to b. Another way to say this is solving Ax equal to b means determining the preimage of b under T. But what does one gain by taking this view? First of all, it turns out that row reduction can be viewed as applying a sequence of linear transformations to both sides of Ax equal to b. And that involves the composition of linear transformations. Second, we'll see how looking at composition of linear transformations guides us towards one way of defining matrix multiplication. In fact, there are many different ways of defining matrix multiplication, but the one that we are going to look at is quite natural in the context of solving systems of linear equations. So let's take two linear transformations. The first one is S of x equals Ax, where A is the matrix 1, 2, 3 in the first row and 4, 5, 6 in the second row. So if you write this out, S of x1, x2, x3 is given by x1 plus 2x2 plus 3x3. That's the first component. And the second component is 4x1 plus 5x2 plus 6x3. The second linear transformation is T of y equals by, where b is the matrix 7 minus 1 in the first row and minus 2, 1 in the second row. So we are now going to look at the composition of these two. In particular, we're going to look at what T of S of x is. So S of x is, as we have seen up here, x1 plus 2x2 plus 3x3 in the first component, and 4x1 plus 5x2 plus 6x3 in the second component. Now we're applying T to this two tuple here. And notice that this is now my y1 and this is now my y2. And I just make the substitution to obtain this tuple. So this will give me 7 times x1 plus 2x2 plus 3x3, the first component here, and then minus the second component, which is 4x1 plus 5x2 plus 6x3. And similarly, we can obtain the second entry. And if we simplify these expressions, we'll end up with 3x1 plus 9x2 plus 15x3 in the first entry, and 2x1 plus x2 in the second entry. And again, each of these entries is linear in x1, x2, and x3, so there has to be a matrix C such that Cx is this tuple. And here Cx will be the matrix 3, 9, 15, and 2, 1, 0. And so, in summary, T of S of x is given by U of x for some linear transformation U. And written in terms of matrices, we can write B, open bracket, Ax, close bracket, equals Cx. And one can indeed verify that the matrix C can be obtained from first computing these columns, BA1, BA2, and BA3, where A1 is the first column of A, A2 is the second column of A, and A3 is the third column of A. And now, if we define the product B times A to be precisely this, then we can write B open bracket Ax close bracket is equal to the product BAx. In general, composing two linear transformations results in another linear transformation, and the matrix that represents the resulting linear transformation can be expressed as a product of matrices, which we are going to define precisely next.